Find the area of steel in the beam in inches squared. In this problem, a singly reinforced concrete beam has a height of 20 inches and a depth of steel of 17 inches. The strain, yield stress, and Young's modulus of the steel are provided, as well as the compressive strength of the concrete, F'C. The beam is simply supported, having a continuous live load of 2,200 pounds per foot. The problem states to use the smallest beam width, B. From axial force equilibrium, we know that the tensile force developed in the steel equals the compressive force developed in the concrete. If we isolate the area of steel term, the area of steel equals 0.85 times F'C times A times B divided by Fs. In this equation, we know the compressive strength of concrete equals 4,000 pounds per square inch. We also know that the stress in the steel equals the yield stress in the steel because the strain in the steel is at least the yield strain in the steel. We can solve for the length A by equating it to beta times C, where beta equals 0.85 because the compressive strength of the concrete is 4,000 pounds per square inch. The length C can be determined from strain compatibility. As is typical, we'll use 0.003 for epsilon C, which is the strain in the concrete at failure. After plugging in the known values, we find the length C equals 7.286 inches, which makes the length A equal to 6.193 inches. The last variable we need to determine the area of steel is the beam width, B. From moment equilibrium, we know the nominal moment in the beam, Mn, equals the compressive strength in the concrete times the distance between the depth of steel and A over 2. If we expand the compressive strength term and then isolate the variable B, we find the beam width equals a quotient involving the nominal moment, F'C, A, and D. In this equation, we already know F'C and the lengths A and D. So we're left to find the nominal moment, Mn. In concrete design, the nominal moment shall be at least the ultimate moment, Mu, divided by the strength reduction factor, B. The ultimate moment for a simply supported beam with a continuous load equals the continuous load, W, times the length of the beam squared divided by 8. The continuous load is a factored load, which equals 1.2 times the dead continuous load plus 1.6 times the live continuous load. From the figure, we know the live continuous load equals 2,200 pounds per foot. To keep the units in pounds and inches, we'll divide that value by 12 inches per foot, such that the live continuous load equals 183.3 pounds per inch. The dead continuous load will equal the density of the beam times the cross-sectional area of the beam. For reinforced concrete, it is typical to assume a density of 150 pounds per cubic foot. The height of the beam is 20 inches, and the width of the beam, B, is unknown. If we divide this product by 12 inches per foot, quantity cubed, then the dead continuous load, WD, equals 1.736 pounds per inch squared times the beam width, B. This makes the continuous load on the beam equal to 2.084 pounds per inch squared times B plus 293.3 pounds per inch. From the profile view, we notice the length of the beam, L, equals 20 feet, which is equivalent to 240 inches. After plugging in the length and continuous load, the ultimate moment in the beam equals 15,005 pounds times B plus 2.118 times 10 to the 6 pounds inches. Next, we'll plug in the ultimate moment, or MU, and solve for the strength reduction factor, B. The strength reduction factor is a function of the strain in the steel, epsilon s, and the yield strain in the steel, epsilon y. The yield strain in the steel equals the yield stress in the steel divided by the Young's modulus of the steel. Looking back, the problem statement provides both of these values, and the yield strain in the steel computes to 0.00207. The strain in the steel is provided as 0.004. Therefore, we can compute the strength reduction factor by linearly interpolating between the 2 points on the plot. After plugging in 0.004 for the strain in the steel, the strength reduction factor equals 0.815. Now we can solve for the nominal moment. By plugging in the appropriate values, the nominal moment shall be at least 18,411 pounds times B plus 2.599 times 10 to the 6 pounds inches. So as to not over-design the beam, we'll change the at most sign to an equal sign. Now we can solve for the beam width, B. We have the nominal moment, Mn, the compressive strength of the concrete, F'C, the length, A, and the length, D. After a few lines of algebra, the width of the beam, B, equals 9.47 inches. Now that we have the beam width, we can solve for the area of steel in the beam. After plugging in the appropriate variables, the area of steel equals 3.32 inches squared. When reviewing the possible solutions, the answer is D.